In this video, we're going to look at repeated measures again, but we're going to add a between subjects variable. This is sometimes called a mixed model because it has both a between subjects factor, in this case lens type 2, and it has a within subject factor, which is axial length at baseline through year 5. So we can start off simply by going to repeated measures. Factor 1, we're going to have 6 years. And we're going to put in 0 through 5 years. And our between subject factor this time is lens type 2. And under options, we have these 3 things. And one of the suggestions when we're doing multiple comparisons with this, before we've always just used the least squares significant difference, which is an unadjusted t-test using the mean square error as a pooled variance estimate for the denominator of the t-test. But because we have this, our years are not independent, they're correlated because it's within a person. One of the things that is helpful for doing the t-test is to make a Bonferroni adjustment. Now in our case, because we have unequal n, this isn't exactly a perfect measure either, but at least it's a start in checking out significant differences. So between different aspects of it. So we're just going to go with this for now, and we're going to continue on and see what we get. Well, we get, we're still split by eye, so we have left and right eye, but now we have the various 3 lens types, aspheric, aspheric good, and poor. We have our multivariate tests, which they're not really that useful until you get into the post hoc. So I think that, and here again we have much least tests of sphericity, which says, are they independent? And they are clearly not. Maybe I'll take a moment and just kind of explain sphericity a little bit. So we have 6 axial lengths. We have AL0, 1, 2, 3, 4, 5 years. Now what sphericity says, remember when we do just regular analysis of variance, we're saying that one of the assumptions is homogeneity of variance. That is, the variances are equal across groups. Well, here we have within subjects. And we want to say that the correlation, we recognize that we have a correlation between factors. And what we want to do is say there is a correlation, and in order to adjust for us, we're going to assume that the correlations are equal. And in this case, in sphericity, when we talk about compound symmetry, we'll talk about that in a week or two, but later, future video. The compound symmetry says we have equal covariance between groups. So the correlation between AL0 and 1 is the same as AL0 and 2, same as AL0 and 3. Sphericity is a subset of that. We say that the difference between, we look at the difference between all the values of AL1 minus AL0, AL2 minus AL0. We go down and we calculate all the differences for all our groups, for all our subjects. And then we calculate the variance of that, 0.08. And the idea is that all of these variances are equal. If they're all equal, then we can do then our sphericity correction is correct. I'd like to point out that these numbers are all pretty large. These are the variances, the variance for each individual year. And these are the variances for the differences between years. Now, those variances, if they were not correlated, should be the same. I mean, the fact that these numbers are so small means that AL1 minus AL0 is pretty close, or that they're close, and the variance is small around that, whereas just taking the overall variance is different. There's no reason to expect these were close, would be this close, if they were independent. They're clearly not. They're much smaller. And so that's the correction that's being made. The fact that these are so much smaller, meaning they're related to each other. And that's why our Mauchly sphericity measure was so significant, because these guys are so different. So 0.000p, and these epsilons, the greenhouse geyser, Hunfeld, lower bound, these are all the corrections that are made to the degrees of freedom and so forth in order to come up with our test. So we have basically gone through, and we see that all the years are different no matter which test you use. Year is a pretty significant factor. Year by lens type, so the effect on year for a particular contact lens depends on the type of lens you're using. And we can look at a picture of that. We come out, we have our expected means. But let's just look at what that looks like. It looks like this. Now, let's think about this for a minute. This is year 0, baseline, up to 5. Now, as I said, this was a matched data set, but it's before we split it. We matched before we split into good and poor control. Notice that the poor controls, this gray line, are lower than this very good controls. That is, kids that had poor control started out worse. You can see they go skyrocketing up, whereas the other kids are sort of flat here. Now, what we don't like about, and you notice also a spheric is in the middle. And a spheric is in the middle because we were matching everybody. So while we split the oranges and the grays, the good and poor control, in general, we matched them so that this is going to be in the middle at the beginning. It doesn't necessarily stay the middle, but at the baseline, it was in the middle. Now, we don't like the fact that these are so different at the beginning. And what we did in our analysis was we included the baseline measure. So what we're going to do here is we're going to get rid of the baseline measure. So we're only going to have 5 values. And so we'll have AL1 to AL5. And then we're going to put in AL0 as a covariate. So, so here we have lens type 2 as the between subjects factor. We're going to look at the first year change and see if there's any differences after we've adjusted for baselines. And so our options, again, we have the lens type, year, and now we can paste this into our syntax so that we can again modify, here it is up here, we can modify and have compare lens type 2 adjusted, and we're going to do the Bonferroni adjustment so that we can use the regular mean square error term rather than a greenhouse geyser adjusted one, and this is basically coming pretty close to a good t-test. Again, our sample sizes are different between groups, so that complicates it a little bit, but this is what we have in this case, and this is what we'll use. So we run that, and we see here we come down to our, let's see, I think I didn't actually run it. Let's try again. There we go. Okay, so we have our tests, and interestingly, when we did the repeated measures, it adjusted by baseline as well. We don't normally want that, but we see that we don't have an effect on the left. Oh, that's multivariate tests. We don't have a significant effective year. We don't have a significant effective year by baseline, but we do have a very significant effect of year by lens type 2. Now remember, whenever you have a significant interaction, you don't really pay as close attention as to the main effects of year or even year with this other factor. So we do see that we have a significant interaction. We look at our contrasts. We look at the contrast within the interaction. This gets a little complicated. We're going to skip that for now. And then we had the within subjects effects. Notice that these are up here within subjects. So these are year. So each subject is the within variable. The between subjects effect are down in another place. I don't know why they don't put them in the same place. Very confusing, but they don't. And so we have the effect of the we're adjusting for baseline, and then we have lens type 2. Also notice very significant. We get our marginal means for the main effective year. Marginal means for the effect of lens type. And then we have the lens type by year interaction. And this is really the one we want to look at in terms of graphing and putting into Excel. So let's look at Excel. We had this one. Now this is what adjusting for baseline, this does that. Now notice, now we're much more similar at year 1. There's an effective year 1, but we're down to, if you brought these down and you still plotted AL0 after adjusting for it, the points would be right here at the 0 point. They'd all be next to each other. And so we still have that big shoot up. It's just that they're all starting from the same point. And we see these guys are very close to each other. Now I've drawn this graph and I've added the confidence bars. Now, before, well, here we have, down here we have our source table. We have our mean square error right there. We have our square root of that mean square error to give us the standard deviation. But notice we're doing it for this sphericity assumed level. We're not doing the greenhouse. We're assuming that they're independent. And we're not using these errors, which in a previous video I recommended doing. If we were going to use those, we would not do a Bonferroni correction. But here, we're doing a Bonferroni correction, and it's giving us a better idea of what the difference should be. It's kind of a robust test to account for sphericity. All right. And then over here, we have taken the standard deviation, and we've divided by the square root of n for the aspheric at year 1, 2, 3, 4, and 5. Notice those are the same. And then we have 57 subjects in spherical good and 37 in spherical bad, and we get those numbers. Now, how do we do a Bonferroni correction? Okay, well, I'm saying that there are 15 comparisons. Really, there's probably there's probably 10 Bonferroni corrections. Well, no, I take that back. 15. We're comparing blue to orange, blue to gray, orange to gray, and we do this 5 times, one for each year. So these confidence intervals are comparing lens type at each year. We're starting with year 1. At year 1, we can see that there is no overlap between either aspheric or spheric good control and spheric poor control. Spheric good control and aspheric are the same. They're actually the same everywhere, but here, and actually these are not quite overlapping either. So there's a difference in growth. The spheric good control grows a little bit faster than the poor control for years 2 and 3, but the aspheric kind of catches up with them, and they're no different. But aspheric or spherical poor control is just out of the park worse. They're just not controlled at all, and they go up. So that eye grows there, where it doesn't grow down here. Now, getting those confidence intervals again. So we're saying we're basing our Bonferroni test on 15 tests. Now remember, our t inverse is 0.16. That's the 84th percent confidence interval with n-1 degrees of freedom. But here I have divided by the number of tests. So it's 0.16 divided by 15. That's the Bonferroni test. And so if we were to look, that t value is 3.31. If it was just the adjusted by itself, we would have a t value of 1.54, but it's 15. So it's a bigger number. And for this example, I use the degrees of freedom of 94, but as we go down, we use it for each of the ones. So I have made this correction, the 0.16 divided by the 15 and n-1. So these are all the t values. And then the confidence interval is just like before, the standard error times the confidence interval, or times the t value. And then just build in the lines there. So that's how we do repeated measures confidence intervals. You need to do this Bonferroni correction and put that in there. In a future video, we're going to do analysis of variance with repeated measures a completely different way, and so that calculating this may be a little simpler. All right, so that's it.